Looks like we're live. Hello everyone and welcome to yet another recreational programming session. How about it? Let's make a little bit of an announcement and officially start the stream. Hello everyone. Welcome. So we're gonna do the usual red circle live on Twitch. And what are we doing today on Twitch at .television website? Today we are compressing images with neural networks, right? So that's what we're doing today. I'm gonna give the link to twitch.tv/soding, the place where we're doing all of that, and I'm gonna ping everyone who's interested in being pinged, and there we go, the stream has officially started. So, what are we doing today? Today we continue working on NN.H, which is a simple header-only library for neural networks that we've been developing for the past several streams. Right, so, and yeah, I'm gonna give the link to this library here in the chat, and for people who are watching that on YouTube, I'm gonna give it in the description, right? So we were doing very simple things with this library, right? So the usual stuff like Zor networks and maybe adder and stuff like that. So on the previous stream, we even implemented like sort of like a UI for training these neural networks. So it's called Gym, right? So this is how, well, I mean, you have to supply the description of your neural network, right? So let's actually start with a simple adder, right? So here this description consists of a series of numbers. It's the sizes of the layers, right? So the first layer is 8 neurons, the hidden layer is 16 neurons, and the output layer is 5 neurons. So this is essentially adder that adds 4-bit numbers, right? So, and then it outputs the sum in 4 bits, and then it has additional bit for indicating an overflow. This is basically how it works. So we're going to supply the architecture of this neural network to the Gym, to the UI application that we developed on the previous stream. And we're going to supply the data for training, right? So it's basically a matrix of inputs and outputs stored in a binary format in the file, right? So, and this is how it looks like. And as you can see, it starts training, it starts updating and stuff like that. So this is actually an old version of the Gym. So recently I updated it, I'm pretty sure. So do I have some changes? So let's actually fetch the latest changes. Hello everyone, welcome. Right, so merge origin master, right? So, and let me rebuild literally everything. So to rebuild everything, I actually need to give the information about Raylib. Raylib is the library that we're using for visualizing and stuff like that, right? So you can find this kind of thing in here. Right, it's actually a pretty cool library. I kind of like it better than SDL, to be fair. I think I'm gonna start using it instead of SDL, right? So it's actually way more simple and way more powerful, right? So the lib we use for visualization, so that's basically what it is, right? So it's a Raylib. Right, so I'm gonna give the environment, right, because I made a custom build of that specific library, right? So, and I'm gonna just rebuild this one more time. And let me start the Gym. So there you go. So now, yeah, I made a little bit of a changes. Like I made, you know, this entire thing a little bit smaller and stuff like that. Added like a bar in here. And as you can see, it doesn't really start training right from the start, right? So you have to press space to actually initiate the training, and it will start training and stuff like that. So I also made it so that you can pause the training at any moment, right? So you basically do the space, right? So, and it keeps training and it's fully trained. So now this is an adder. There's no, unfortunately, like a way to verify that it works, but trust me, it works, right? So you can here also restart at any point, right? So this is a very convenient UI that also shows you the state of the weights and biases of the neurons, right? So, and it trains this entire thing, which is actually kind of cool. It's a pretty cool visualization, right? So all of that is toy examples and stuff like that. So today I decided that the time has come to try to do something more serious, right? The time has come to do something more serious, and I wanted to try to do something that I think we discussed a little bit on our Discord server, right? So we started the discussion with, can you make a function, two variable function, right? So let's actually start with the following thing. So maybe I need to start up my pane so I can draw and stuff like that. Right, so let's actually see. So we have some sort of a function, and it's a function of two arguments, and x and y, right? And it gives you the like a value z of some sort. Can you craft a function that acts like a certain image? Right, so essentially, if you basically try to plot it, right, and you use z as sort of like a maybe like a height or like a brightness, will that function result in some sort of an image, or can you like encode an arbitrary image and stuff like that? And what's interesting is that this is what you can use neural networks for. Right, you can basically craft a neural network, right, with two inputs, right? So you can say, okay, so this is the X input, and this is the Y input. Then here you can have some sort of like a hidden layers, right? Something in here doesn't, we don't know what it is. So you're supposed to put some sort of like a sparkles in here, right? So you're supposed to put sparkles. So recently sparkles, kind of like a sparkles emoji became an unofficial symbol of AI. In all of the UIs, UI designers, every time they make a button that enables AI, they put like a sparkles emoji in there. So sparkles is basically an unofficial symbol of AI. Right, this is actually kind of funny. So you put X and Y in here, right? So you put X and Y, and as an output you can have the Z. Right, and essentially you can take any image, right? You can take any image and use that image as a training data for that neural network, right? So essentially you can basically take a pixel, right? You can take X and Y of that specific pixel, right? X and Y of that specific pixel, and set the brightness in here, and you can use it as a training set and train neural network to behave like that specific image. So what will effectively happen, theoretically, is that it will take the image and it will store that image inside of that neural network somehow, right? It will store it somehow. And what's interesting is that we can try to give it like way less neurons than we have pixel in an image. And so if that will work, what will effectively happen is neural network compressing the image into itself. This is actually very interesting. Right, so if it's going to be like a, you know, less weights and biases than the pixels in the image, it will have no way but compress this entire thing into itself. But what's interesting is that X and Y are continuous. They are continuous. So that means you can even look for the values of this brightness between the pixels. And the neural network will probably approximate it. So you can not only compress the image into the neural network, right, theoretically, we don't know that yet, but you can also upscale it, right? You can also upscale it. You can even basically take all of the coordinates like of this thing and normalize them from 0 to 1, right? You can normalize them from 0 to 1 and train it on 0, 1, right? So this is going to be 0, 1. And then that way you can basically reshape it however you want, right? With any size, and it will just sort of approximate and stuff like that. So you can even like probably do colorful images, right? So instead of like brightness, you may try to return RGB, right? Like this. But I don't want to go into colorful images yet, right? So because I'm afraid of maybe like too many complications, I really want to start with something simple. So we're gonna have like a grayscale images, right? So does it make sense? It actually sounds like a very interesting idea. Let's go ahead and do that, right? So we're gonna work with grayscale images, right? So, and I not only wanna do grayscale images, I also wanna start with very small images, right? So we're gonna start with a very simple example, a very small grayscale image, right? So where can we find an interesting grayscale small image, right? So we can just use MNIST Database, right? So MNIST Database. And it has a lot of these handwritten digits, and they're basically 28 by 28, right, there you go, 28 by 28 grayscale images, right? So let's actually try to find it. For some reason it's is that the official website? I'm pretty sure. Yeah, okay, so let's actually go ahead and try to do that. So there's some images in here, right? So let's download them. So they split it in two sets, right? The first was set for the training and the second set for validation. We don't really need the whole set. We just need one single image from that, right? So let's actually go to nn.h and let's just like try to download that and see like how is it going to go. Open game art, but we can also try to use open game art at some point. Right, so this doesn't look like a tarball. Wait, is that literally like a single file zipped or something? Like, okay, so can I just Emacs recognize that? Yeah, it's literally single 45. Okay, so okay, they probably took all of the images and compressed them into a single file, so we'll have to extract that stuff somehow. Yeah, it's just like literally data. Maybe there is a version with PNG. No, I didn't really see that. Is there something like MNIST PNG? Because I don't really want to spend time extracting all of that scheisse. Kaggle actually has something. Okay, so let's take a look at that. So can we get something from here? Okay, so there is a couple of folders in here. So here's the training and oh, they split it into like digits in here. So which digits should we pick? I kind of like 8, right? So because it has like these two loops. This one is actually kind of cool. Yeah, this one kind of cool. Can I get that? So this is OpenPNG. Now I wanna... You see how small it is? It's literally 28 by 28, right? So we're gonna try to train a very small, simple neural network that should behave like this 8, right? And we'll see if it's gonna work or not. I think it's kind of interesting. Right, so can I can't press right click because of that stupid bug of Chromium or something where I have to open a separate application, click right click so it shows the pop-up, and then I can finally do that. Like, it still persists for some reason. I don't know why this happened. It's so weird. Okay, so we're gonna copy image address. Right, so I'm gonna double get. Can I just save it though? Save image as. All right, so let's save this thing. And maybe I'm going to go to the download folder and find this entire thing in here. So here is the image. You can see how small it is. Right, so that's the simple image. Right, so I think I didn't acknowledge the like subs and stuff like that, and also we have some beats, so let me quickly acknowledge that. So there's a couple of things in here. Right, so there are people subscribing off screen. 21 Lux, Bora King, Bike Shatter, Yath XYZ, I always see. Thank you so much for all of the subs. Unconventional Coding, thank you so much for tier 1 subscription, and thank you for 100 bits with the message, I enjoy watching your videos while unironically coding PHP. I mean, there's nothing wrong with PHP. Like, to be fair, I programmed in PHP recently, right? So I wrote like jokingly a compiler for C in PHP, and I didn't really hate that language that much. I do hate all of the languages equally, but I didn't hate PHP that much, and I could see myself actually programming in that language for money. So that wouldn't bother me. So I see nothing wrong with programming in PHP, honestly, right? To me, it felt like, yeah, yet another scripting language. I've seen dozens of them throughout my career as software developer. I've seen dozens of scripting language, and it's just like, yeah, it's yet another scripting language. Not the worst one I've seen, honestly. the conversions of like strings to numbers is a little bit weird, but you're not supposed to use double equals anyway, right? So you're supposed to use triple equals. And on top of that, the latest version of PHP has like a stronger typing and even type hints and stuff like that. So I can see that as a usable language actually. So I didn't see anything wrong with that. So yeah. So anyway, right. Let me see. So what we need to do we need to convert this image into the data file, right? So because the way our gym works, right, so it accepts the data file in here. So one of the things we have to do, we need to be able to like convert this entire image to this data file so we can give it to the gym, because gym doesn't really support images at all. Right, it doesn't support them. So let's create a thing, let's call it maybe PNG to mat, right? So that sounds like a good name for this thing, right? Right, so we're gonna create std. We're gonna include std.io, and we're gonna simply accept the arguments, right? And so essentially we're gonna accept the path to the image through the arguments, right? So how can I do that? I need my trusty shift argument function. So I think I do have it in Gym. Yeah, here it is. It's a very useful function, right? Which essentially sort of like pops the arguments from the left, right? You can think of the arguments as an array of arguments that is provided through command line. And essentially what this function does is just like pops out like the first argument and decrements the amount of arguments, and increments basically goes to the next argument. And it's very convenient, right? So essentially the first argument in here is always the program. So which we can do args shift, right? And we can do argc, argv, there we go. So, and it's like very useful for usage messages, right? So, then we can check, okay, do we have any arguments in here? If we don't have any arguments, we have to say something like std error, no input file is provided, right? No input file is provided. Right, and we're gonna return 1 in here, and on top of that we can also print the usage, right? So we can say something like usage as input png, right? So there we go, and we have to provide the program. So let's actually go ahead and compile this entire stuff. Let's compile this entire stuff. So this is gonna be png to mat, right? png to mat. So I don't really want to build everything. I only want to build PNG to mat. Right, so let's actually do it like that. And it requires raylib. To be fair, raylib is only needed for gym, but for some reason I made it so like every executable in here requires that. So I think I need to change that. So because in here I only need lm, right? So only this thing needs raylib. Right? So let's actually do it like that. And oh yeah, and it needs it because it cannot evaluate this line, right, if it doesn't have a raylib in here. Okay, so maybe one of the things I have to do, I have to move this entire stuff in here, right? So maybe I'm gonna only leave the mathematical library in the libs, right? So like so. So here we would have everything related to raylib, and then the common libs in here, like so. And for the C flags, yeah, I think I also need to move this entire thing only to the gym. Right, so in C flags and libs, we're only going to keep things that are common for all of these executables, right? So only the things that are common. Okay, so, and it complains about something, implicit declaration of assert, which is understandable, right? So we can include assert in here, sure. And it worked, right? So if I try to run PNG to mat, it complains that we didn't provide an input file. If we do provide an input file, right, so we provide the image in here, it doesn't complain about anything. It doesn't complain about anything at all. So what we need to do, we need to read the goddamn image, I suppose, right? We need to read the goddamn image. So we're gonna use stb image, right? So that's usually what I use for reading images in C because it's so goddamn convenient, right? So let's do nothing's stb. So where is stb image.h? All right, so recently GitHub changed its UI, I think, or it didn't. I don't know, like, because I started to see that it created this panel on the left, but I saw that on my different account and I don't see that on this account. they either change something right before the stream, or this is A/B testing. Right? Do you guys know what is A/B testing? Right, so it's essentially when you implement a feature for an application, you don't enable feature right away. You essentially show that feature only to half of the users, right? And you measure their reaction and compare it to the reaction of people without that feature and make a decision whether actually to roll out to everyone. So maybe that's basically what it is. So I don't know. So here it is closed, but oh, okay. So we have this thing. Oh, that's the panel I was talking about. Interesting. Right. Weird. I don't know why it's needed. But it is what it is, and it isn't what it isn't. Okay, so let's actually download the library in here. So STB image. Okay. So now let's include this entire stuff. New UI is BS. Well, any new UI is actually BS, right? So every time like any website comes up with a new UI, everyone doesn't like that. And the reason why everyone doesn't like that is because everyone is like already developed habits on how they use the website, and changes in UI actually break those habits. It's actually kind of interesting, right? Because we are so obsessed about backward compatibility with programming interfaces. But when it comes to user interfaces, nobody gives a shit about backward compatibility and existing habits of the users. Like, fuck users. Seriously, fuck those people. Right, so it's kind of interesting, like, why nobody like cares about backward compatibility of like existing habits of the users? It's just like, and what's interesting is that you do have information about the habits of the users. You have telemetry and stuff like that. You could have at least respect that. I don't fucking know. So, yeah. I guess we just respect computers more than we respect humans. And the latest AI hype actually kind of confirms that. Anyway, so what I was doing, I wanted to just include, STB image page. Right, so... And let us see. So we're gonna do stbi load, and this is how we load the images. So I suppose the first thing I need to do, I need to actually grab the path to the file, right? So we have to do something like const char. So let's say image file path, right? So this is the image file path. I don't really know why I say it's supposed to be PNG. Because STB image actually supports not only PNG. Right, so it's kind of like misrepresenting what it actually is. So let me actually rename this entire thing. I think it has to be called image to mat, right? So, and let's do build.sh, and I'm going to replace PNG. I'm fucking tired. Excuse me. So let's continue. So this is the image to mat, right? So that makes sense now because it's not only PNG. And here we have args shift, right? So we're shifting and we're getting the file path, right? So argc, argv, there we go. So and in here, what we need to have, so x is actually image width, right? So it's an image width. And here it's image height. So what n usually means is the amount of components in image, right? So essentially it's the amount of bytes per pixel, right? So that's what it is. It's amount of bytes per pixel. So if we take a look at the actual definition in here, right, so it's the comp, right, so the amount of components. So by passing it by the pointer, it actually gives us the actual amount of components, right? So, and in here we provide like the one that we expect, and if I remember correctly, STB image can sort of like adapt this entire thing for us, right? And if we provide 0, it will just not convert to any of the desired components, right? So I think it's kind of important for us because what we care about is that the image is grayscale, right? Is the thing actually grayscale? So let's actually see. Right, it's 8-bit grayscale. Okay, that's actually pretty cool. So essentially, we can condition on this specific thing, right? So we can check that this thing is supposed to be equal to 1, and if it's not equal to 1, we can say that we do not support that, right? So we only support grayscale images and stuff like that. Right. So yeah, so essentially let's put image width, right, so and then image height, and this is image components. There we go. So and in here we're gonna have image pixels, right, and since it's a grayscale 8-bit image, we're gonna actually have a pointer to uint8, right? So we're gonna also cast this entire thing to uint8. Right, and we can also check that this entire thing is not equal to 0. If it's equal to null, right, equal to 0, we're gonna say that we did a fucky wacky, oopsie doopsie, error, could not read image as image file path. I'm gonna return 1. There we go. So, and another thing we can do in here, we can say, okay, if image components is not equal to 1, right, if it's not equal to 1, we're also going to say something like, right, the image s is, has, let's put it this way, d bits, image s is, let's put it this way, this thing is this bit's image. Only 8-bit grayscale images are supported. That's what I wanted to say. Okay, so image file path and the amount of bits. So as far as I know, it returns the amount of components. So its amount of bytes, we need to convert it to bits, so it has to be 8. Right, so this thing is this bit image on the 8-bit grayscale is supported, and we're going to return 1. So after we checked all of these things, we can say, okay, so this is image. Size is going to be d by d. And then something like d bits, right? So I think that's reasonable. So image file path, then image width, image height, and image components. Do I see components? Here are the components, and I'm going to multiply it by 8, and there you go. So let's try to recompile this entire thing. Is it going to work? Okay, so this is supposed to be image file path. Any other errors? I think everything should be okie dokie, a karaoke, almost there. I think I need to disable O3 because it just takes too much time to actually finish. Right, because it's just like full optimizations and stuff like that, and I'm also streaming on this machine, right? So let's actually put maybe 2 in here, and it especially makes it slow because of the STB image. There's a lot of code in STB image, right? There's a lot of code in here, well, 8,000 lines of code, and it's just like trying to fully optimize all of them, right? This is a single file, so because of that, it kind of compiling STB image with O3 like significantly slows everything down, and especially on my 10 years old laptop, from which I'm also streaming, right? So so that's why it's a bit slow. But anyways, so if I try to use less optimizations, I think it's going to be a little bit faster. Not really. O2 is still kind of slow. What if we don't do any optimization at all? Let me see. It's actually way faster, as you can see. Yeah, there we go. All right, so let's see. Okay, so let's provide the image in here, and there you go. So this image size 28 by 28, 8 bits, and that's precisely what we expected. Isn't that cool? Isn't that poggers? I think it's cool and poggers simultaneously. So I think we had some other images in here. Yeah, we had the thumbnail, right? So I put that thumbnail in a README. So this is definitely not 8-bit image, right? This is definitely not 8-bit image, so we can try to supply it in there. So this is the thumbnail, and it should crash saying it's a 24-bit image, only 8-bit grayscale images are supported. That's right. So we're rejecting everything that is not 8-bit in image. Okay, so that's cool. So we have the this entire thing. Right. So the next thing we need to do, we need to actually convert that to a training data, right? So we need to convert it to training data. So let's actually include our trusty framework that we developed ourselves, nn.h. And let's define nn implementation to make it act like a C file, not like a header file. Right. So, and let's construct a matrix, right? So let's construct a matrix. It's going to be mat. And it's going to be like a training data. I usually like to call it T. And let's allocate. So what's going to be? So the amount of rows is the amount of samples. So we can say that each pixel of the image is going to be sample of the training data, right? So each pixel. So that means the amount of rows is going to be image width multiplied by image height, right? So that's basically what it is. And the amount of columns is essentially the amount of inputs plus outputs, right? So essentially how we organize the training data within the matrix, right? So essentially you allocate rows, and each row in the matrix is a training sample, right? This is a single training sample. And then you have a couple, like several columns which correspond to the input and several columns that correspond to the output. So you store inputs and outputs within the single row. And what is considered input and what is considered output greatly depends on the architecture of your neural network. So essentially you supply an architecture of the neural network, right, like so, adder.arch, right? So here the input, we have 8 inputs and 5 outputs, right? So that means together the amount of columns in the training data is going to be 13 elements, right? So basically you just sum them up. So in our case, the amount of columns is going to be 3, right? Because first thing you have is x, which is x coordinate, then y, and then the basically the brightness of the pixel, right? So essentially what we have to do, we have to turn all of the pixels into these sort of triples and just store them, right? So that's what we have to do. Yes. So we've got some more bits from Enumerate. Thank you so much for 100 bits with the message. I really enjoyed your TypeScript videos. By the way, I had some nice ice cream today, so here are some bits so you can enjoy my epic ice cream club. Okay, thank you so much. Surprisingly, I'm like, when I say that, people cannot believe me, but I don't like ice cream. I'm a really weird person. I really don't like ice cream. And it's not like something recent. I never liked ice cream since my childhood. Imagine, like, my peers were considered me weird, and other adults were considered me weird because like a child doesn't fucking like ice cream. What the fuck is wrong with you? Are you even normal? But here's the interesting thing. If the food is cold, I can't taste anything. Ice cream is literally tasteless for me because it's how cold it is. Like I can't taste anything. It's just like tastes like nothing. This is the first thing. Second thing is that I have a very sensitive teeth. So eating ice cream is literally painful for me. It's like not really painful, it's extremely uncomfortable. Imagine eating something extremely uncomfortable and tasteless. That's what it feels for me eating ice cream. So yeah. But I'm really glad that you enjoy your ice cream. I'm not saying that ice cream is bad. It's just like I'm saying that I'm a weird person. Right, so for me, it's just like something that is very uncomfortable to eat and doesn't taste like anything. So the only way I enjoyed ice cream is just actually by melting it down and drinking, right? Because that way it wasn't that really cold and I could actually taste something, right? So yeah, it tasted sweet and stuff like that. Yeah, thick shake, yeah. Yeah, I tried it melted before, yeah. You live in a cold country, you want something more, I guess. Yeah, I guess. I live specifically in Siberia, which is like extra cold part of Russia, right? So, Siberia is actually weird, honestly, because specifically in the place where I live, the temperature range throughout the year is -30 Celsius and +30 Celsius, right? It's a really weird place. Anyway, so let's continue. So here we're supposed to have three columns on this entire thing. Okay, so let's go ahead and iterate each individual pixel. Right, so I'm gonna start with y. We're gonna iterate the rows less than image height, like so. And we're gonna iterate the columns. Right, so it's gonna be image width. So here's the interesting thing. As I already said, I want to actually, you know, train on the normalized coordinates, right? On the normalized coordinates, basically the coordinates from 0 to 1. Right. So the way you can convert any coordinate to a normalized coordinate, right? So for instance, you have this sort of x, and you have this width. So essentially what you can do, you can just take x and divide by w. And that way you're gonna get a value from 0 to 1, right? So the closer the x to 0 to here, it will be closer to 0. The closer the x to that h, the closer is going to be to 1, right? So that's what being normalized mean, right? So, and you can do the same thing for y coordinates, right? And what's interesting is that by doing that, you kind of lose aspect ratio, but it also allows you to remap it to any sort of shape and size of the image. So, and the reason why I do that is because once I train this neural network, hopefully I'll be able to upscale it, right? So it's 28 by 28, and what I want to be able to do, I want to maybe upscale to 520 by 520. Yeah, it's basically LERP, right? It's basically linear interpolation, right? So it's kind of like a halfway to linear interpolation, right? So linear interpolation is actually also includes a step of mapping that normalized value to a different range, right? Basically, I don't know. It just like depends. Anyways, so we will need to work with normalized coordinates. How can we do that? Let's actually do something like an x, and this is where we're gonna just take an x and divide it by image width. Right, but what's interesting is that this implies that x can be equal to image width, but as you can see, it can never be equal to it. Right, so, and essentially what we have to do, we have to basically divide it by image width -1, because that's the maximum value x can be, effectively, right? And all of that makes sense if we convert that to floats, right? So all of that has to be floats. So this is also y, and this has to be height, right? So there we go. All right, and what we want to do is we want to probably get the actual pixel, right? So essentially we have to do image pixels. Let's do y multiplied by the size of the row and plus x. Let's actually print those pixels, right? So it's actually a very small image, 28 by 28. So that means we should be able to actually do some ASCII stuff. So that should work out, I think. So let's do printf. So u, maybe we can make it like the width of this entire thing 3, right? So we're gonna actually do a little bit of a left pad, right? And there we go. So we can do something like this and just like printf n, and we should be able to see that image, right? So not that image though. So let's actually also do build sh, and let's do this thing. Is it going to work? Yeah. Does it look like 8? It's kind of difficult to see because of these zeros. Maybe we can do some other choice. So maybe we can pad with spaces. I think padding with spaces is gonna be... Yeah, look at that! Yo, this is 8! What the fuck? So we got some sub. Thank you so much, Amoy for tier 1 subscription. Thank you, thank you, thank you. So that's the image that we just read, right? That's pretty poggers. That's pretty poggers, not gonna lie. Okay, so what I want to do, I want to take this entire thing. And as you can see, these are the values from 0 to 255, right? So which means that we can also normalize them, right? If we take these values and divide it by 255, we're going to get the values from 0 to 1, right? So normalized values in, normalized value out. Makes sense. And that way we can remap this thing to like anything, right? So I think that makes sense, right? So let's quickly do that. So we're going to just divide it by 255, but it's going to be float. So since this is a float literal, this entire thing is going to be converted to floats anyway, so we don't have to worry about that. So this is a normalized brightness. And essentially what we have to do, we have to just store that in a current row. But what is a current row? What is the index of the current row? We can just basically take, yeah, we can do a similar thing. We can say that this is a row. Yeah, there we go. So we can just say this is the index. So this is going to be I. So this is I. We can put it in here. And we can do a similar thing. Mat at T. So the row is I. And the column is actually 0 is going to be corresponding to X. 1 is going to be Y. And 2 is going to be B. And in fact, we can just right away just assign those values in here. We don't really need intermediate values, I think. I didn't see any point in having these intermediate values. Yeah, that makes sense. Yo, there we go. So let's actually print this entire matrix and see if it looks like anything, right? So there should be like a 700 something, right? Okay, so here is the matrix. Yeah, there we go. So we can see some like patches of like bright colors and stuff like that. Yeah, so that's basically the image, right? So that's basically this image from MNIST, but encoded as a matrix for training, right? So we converted it into training data. So that makes sense. So now we have to save it to a file system, right? I think there was something like mat save. And it accepts the file, right? So the output file. So let's actually go ahead and just try to do that. So we need to open the file. Fopen. So let's say out file path for writing in binary. So const char out file path, and it's going to be equal to img.mat, right? So I think that's the reasonable name to call this entire thing. And if this entire thing turned out to be null, we're gonna do fprintf std error. Error could not open file as for whatever reason, right? So I'm gonna return 1. All right, so and then we're gonna try to save the matrix in that specific place, and once we successfully done that, we can say something like generated as from s, which effectively means generated out file path from image file path. I want to actually print both of them so we can clearly see what was generated from what, and there you go. Right, so let's actually go ahead and do that. Okay, so generated image mat from this thing. Do we have image mat? There we go. So it's almost 10 kilobytes. Almost 10 kilobytes. So, okay, so what's cool is that now we can put that shit into the gym. Right, but before we can do that, we need to define the architecture of the neural network, right? So we have 2 inputs and 1 output. I'm pretty sure we won't be able to train anything with this kind of stuff, but we can try, right? We can try to do that. So let's go ahead and do that. Gym, and let's provide, so image architecture, image mat, right? So let's actually run that, and there we go. So this is the neural network that we can try to train, and it doesn't really go anywhere, right? So it went through 10,000 iterations without achieving anything. It's just like, yeah. So it has no place to store all of that image. So let's actually put some stuff in there. So how big of the inner stuff going to be? So it's 28 by 28. So let's actually put 28 hidden layer in here and see if it will be able to basically compress like all of the rows into a single row somehow. Will that work? So let me see. Okay, so this is where we can try to store that image, maybe. And let's see if it's going to do something. It doesn't really go that much, right? Yeah, it doesn't really. Oh. What the fuck? It's doing a jeep and it's. Yo, what the fuck? It learned something, but we have no way to verify that and see. We like, yeah, the gym is kind of scuffed. Is that because it doesn't allow you to sort of like store the trained neural network? I can add that, but here's an interesting thing. I don't like this workflow. I really don't like this workflow where you have to write a separate program that generates data and import data into a separate file. Then take that file into a different program, train this entire thing, and it will spit out a new file. And now you have to write another program that takes that trained neural network and verifies it somehow. And it's just like, I want this to be a single thing, right? I want this to be a single thing. And maybe what I have to do, instead of gym being like a separate program, maybe gym has to be also part of the library. You know what I mean? So it would be kind of cool if from the sort of same program in here, image to math or something. Okay, I generated the training data and then I would say, okay, gym, and I just provide the training data, and maybe also like I allocated the neural network, right, and then a log, all right, and then a log. So, and it would say something like architecture array len architecture, and then size t, and it would provide the architecture something like 228 1, right, and then I would say, okay, train that neural network on that data, and it will start this thing. And then I close the window, and then here I can verify this entire thing with the data and whatnot. Right. So it would be kind of cool if it was just a separate component. All right. Okay. People are getting really inspired to program in C for some reason. Yeah, I keep receiving messages that I somehow inspired people to program in C. The reason why I program in C is not because I like this language. I actually don't like this language. I think like it has a lot of flows and stuff like that. But the reason why I program in that language is because it's the only language of its kind. Right. Because it's the simplicity of this language. Like no other language actually provides this level of simplicity. Everything else is overcomplicated, over-engineered, slow, and stuff like that. And C is the only thing that is just like doesn't stay on my way, but it has a lot of problems that makes you shoot your leg quite often. And I wish like there was a language that kind of like C, but actually addresses all the problems of C. So far, the only language that I've seen that is like that, which is as simple as C, but also addresses the problems of C, is Jai, but it has a huge flaw. It doesn't exist. So, well, I mean, I do have a compiler of Jai, right? But as already said, I can't just like really easily share the source code I wrote in that language because not everybody has the compiler. Though the compiler beta is expanding. So the more and more people actually have an access to it, so maybe at some point it's not going to be a problem. Isn't Go kind of simple? Nah, it's not as simple as you think. It's like C, but with very specific things put on top of C to solve very specific Google problems, right? Anyways, so, okay. So I use C because the things I do are not about programming language. The things I do are not about programming. We should stop learning programming languages and start learning programming already instead of programming languages. So I want to be able to do something like that. So, but I'm kind of lazy to actually start working on the gym. What if I just like do this entire stuff without the gym? Yeah, there we go. I can just train it myself, right? So I can just allocate the neural network, like so, right? The neural network. And then I can allocate the gradient, right? And I can just train this entire thing. So I can just train it for like 10,000 epochs, and then I can try to, maybe I can try to print the output of the neural network in ASCII, right? Just to see, because I want to see how it's going to look like, right? So it would be kind of cool to see how it's going to look like. All right, so we're going to do backprop, right? So where's the backprop? I want to see the signature, right? There we go. Oh yeah, okay. So we need to split our training matrix, right? So we need to split our training matrix into the input matrix and output matrix. Okay. So let me quickly try to do that. So we're going to have an input. An input basically has the same amount of rows as the original thing, right? So this is going to be rows. The columns is going to be 2 because we have 2 inputs. Stride is going to be the same as the original thing. A stride is basically how many columns you have to speak to get to the next row. Right, and since we store inputs and outputs in the same sort of matrix, right, so you have to sort of like jump over the outputs to get to the next inputs, right, if that makes any sense. Right, and then here the actual data starts at a matrix 0, 0, so this is where it starts, at least for the input. Right, so the outputs are going to be like this. So the rows is the same as the original. The columns is actually 1, right? So it's basically a huge single column. Right, stride is also the same, right? So this is how many you have to skip. But we start at slightly different place, right? So in terms of row, it's 0. So 0, 1, I think 2, right? So maybe we can even do something like, this is where you have to start, so it has to be maybe TI calls. So that's actually kind of useful, because if I modify the amount of columns, right, it's going to be 3, I never have to modify this specific part. I think that's actually kind of cool idea. All right, so, and we can try to print those matrices to see if it actually like sort of worked out the way we expected it to work out. So I'm gonna exit in here so it doesn't go down there and doesn't start like saving and shit. So, and let me rebuild this entire thing. Okay, so it didn't compile because this has to be a pointer. Thank you, compiler. Very cool. All right, so we've got this stuff. So this is the inputs, which are just coordinates, and these are the corresponding values. So there is a lot of 0, but there's some patches of like, you know, bright things, and that actually corresponds to the image, right? That's actually corresponds to the image. Okay, that's cool. So let's not save this entire stuff to file system anymore, because we're going to be training it like right here. So what we have to do, we have to provide the neural network, the gradient, the input and output, right? And that will give us the gradient, like where we have to move. And the next thing we have to do, we have to learn from that gradient, right? So essentially we have to subtract that gradient from the neural network with a specific rate. Right, so we take the neural network, we subtract the gradient, and the rate, let's set the rate to 1 for now, right? So this is going to be 1 for now, and we'll see how it goes. All right, so let's train this entire thing for, I don't know, for maybe 10,000 epochs, right? Epochs. I forgot where you put stress again. Max epochs plus epochs. Yeah. Doesn't autocomplete for some reason. Okay, so how many we're gonna have in here? So let's say it's gonna be 10,000. I think that makes sense. So we can also print the cost function, the actual value of the cost function. Right, but we don't want to print it all the time, because it's gonna actually clutter the output and it will slow down the entire thing. Right, so we want to print it maybe every like 100 iterations, or maybe every 1000 iterations. I think that makes sense. Right, so we can print the iteration in here and then the cost function in here. So the iteration is epoch, I don't know why I call it epochs, because it's a single one. It's more of a current one. It should be just a single form. And let's say that if this thing is divisible by 1000, only then we're gonna print it, right? So we don't even compute the cost function on each iteration, only every 1000 iterations. What we found is that it's actually kind of fast. It makes it go brrr, makes it go brrr. So is it gonna do the thing? And it kind of, well, it's actually going kind of slow. It's not going anywhere for some reason. Oh yeah, I know why. Because I didn't randomize the goddamn neural network. Right, so because it's all zeros, so of course it doesn't learn anything. Right. Okay. Rand, and then from -1 to 1. Let's actually initialize it from 1 to 1. And I think 1000 is too slow. Let's actually do 100 instead. There we go. So it is learning. It is doing things. It's kind of interesting that it's stalling for a little bit. Right, it is stalling for a little bit. It actually feels a bit slower. Well, I mean, yeah, that's fine. So, but towards like 10,000, it should actually start like dropping down significantly, as we observed in Gym. As you can see, it's going down. I think by 10,000 it's gonna actually get somewhere. I guess it's fine. All right. So it started somewhere close to, yeah, it actually went up a little bit. It went up a little bit, and only then it started to, yeah, that was interesting. Anyway, let's try to verify. Yeah, we also probably need to enable the compile optimization. So yeah, so let's try to verify this entire thing. We're gonna do y starting from, yeah, let's actually do the original size, right? So image height, right? And then we're gonna do size X. So how we're gonna be actually rendering the neural network, right? So we need to render the neural network somehow, right? So essentially, we need to take the input of the neural network, right? And it's a row, right? So it's a simple row, and we need to take a column, 0. So the first one is going to be x. So what we have to put in here is just float x divided by image width -1, right? So that's the first input, and then we have to put y in here. And there we go. We actually initialize the inputs of the neural network. So the next thing we have to do, we need to forward all of these inputs. And in the output, we have the output of the neural network, right? But it's a matrix, but it's a 1-by-1 matrix, right? So what we have to do in here is probably get the value at 0, 0, right? It's a 1-by-1 matrix. And that value is going to be the brightness from 0 to 1. So essentially what we have to do, we can convert it to a value from 0 to 155, right? So multiply it by 255 and just like save it to, you know, pixel. So this is our pixel. And in here, we're gonna just like print it the way we printed it before, right? So this is a pixel. And in here, we're gonna print a new line. So we literally just put the coordinates into the neural network, we forward it, we get something back, and we treat it as the brightness of the pixel, right? So let's see how it's gonna work out. So on top of that, I think it makes sense to actually enable the optimizations as much as possible, so it goes a little bit faster. So there's something wrong in here. I'm not really sure I like that. This is because these things are integers, so I think it makes sense to convert them to size t. I don't really like warnings. Okay. So we've got some subs. Y Software, thank you so much for Twitch Prime subscription with the message have a nice day. Have a nice day to you too. Thank you so much. All right, so it is compiling, right? So it is slow because I have a slow laptop, and it's going a little bit faster. So yeah, thank you so much for suggesting to make it go a little bit faster. That's actually fun. I mean, it does look like so the cost function is actually still kind of high, but it's a very interesting approximation of the original image. So I think we need a comparison, right? So I think we need a little bit of a comparison. So let's do a second thing in here, right? So where we basically do the same, right? But with an original pixels, right? Image. So image pixels, right? So y multiplied by image width, right? Plus x. And here we're gonna do printf. So one of the things I probably don't want to do, to be fair, is printing this stuff. Right. Looks like a donut. Yes, it is. It is what it is. It is a donut. It would be cool if the gym showed image in real time as a neural network. Yeah, it would be cool, but that means like gym is supposed to be like a very generic thing, and not all the neural networks are about generating images. So how do I feed that stuff into the gym paradigm? Okay, so here's our donut, and here is our original 8. And it's kind of close to the original shape, if you know what I mean. If we let it train for a little bit longer, maybe it would become that 8. You know what I mean? That is kind of cool. So another thing I want to do is probably maybe filter out things that are 0. That would be kind of interesting. So if I put pixel in here like that, if pixel, and then if pixel. Add more layers. Nah, I don't think the problem is with layers. I think we just need to let it train for a bit longer. I think we need to let it train for a bit longer. Okay, so it's doing things, unimaginable things. Oh my god. Okay. Yeah. So let me see, where is that? God damn it. That's very dumb. Right, so essentially what I had to do instead is just like print, you know, spaces, 1, 2, 3, 4, right? So that's what I forgot to put in here. Right. Yeah, there we go. So that should be there. Could also show the result in certain intervals to see the progress. Yeah, it would be kind of cool. Yeah, it would be nice to see like how it actually learns, right? How it actually learns. So that's what that's what I wanted to see. Right, it's actually spread out like a lot, right? So you have like a very low values in here, right? In here where you have to have zeros. Okay, let's actually let it run for a little bit longer. What if we have like 10,000 of iterations? What if we have 10,000 of iterations? So we got some more subs. Sin2s, thank you so much for Twitch Prime. Thank you, thank you, thank you. All right. So twice as more iterations. Man, I need to, yeah. Maybe I just need to copy paste the gym into this application. All right. Okay. It figured out to put zeros in here, so it's doing something. That's pretty cool. So you know what, like I don't like this interface. I really got used to gym, and I think it's really super convenient, right? I really like the fact that you can just like restart and just pause and stuff like that. It's just like, yeah, it's very convenient. So you know what I'm gonna do? I'm gonna actually literally copy paste gym into our application, and at some point I think I'm gonna move towards making gym a library, a separate library that you can just call to when you want to start that UI. I think that makes more sense. That makes way more sense in my opinion. All right, so what we need to have in here is and then .h. Well, I mean, I already have everything. So let me start maybe from main, right? So here we do this kind of stuff, we prepare the data. So it's pretty much the same as like a original thing, right? So what we have to do in here is just this. Yeah. And it's actually, this is the entirety of the gym, basically, almost, right? So it's like, at least this is the main loop. Right, at least this is the main loop. So, and instead of this thing, I'm gonna put this thing in here. So I think what I'm gonna do, I'm going to just go through the compilation errors. Okay, so let's do compiler assisted refactoring. So to speed up the compiler assisted refactoring, I'm gonna disable all of the optimizations and I'm gonna just like run this entire thing. All right, so let me see. So we need to include the raylib, right? raylib.h. Okay, so it cannot find that because we're supposed to use this stuff, right? So put it in here, and all of the libs in here as well. So this is going to be libs. There we go. So it still can't find it. Oh, this is because I have to do the environment, right? Because it's in a separate environment. Right, there we go. So what do we have in here? Window width. Okay, so we need to bring the window width and window height in here. Though I think I'm not sure if I want this thing to be like a you know, global constant. So I'm gonna actually make them like a local variables like this in here. I think that makes a little bit more sense. That makes a little bit more sense. Okay, so let me see. So cost plot, and all right. So let's actually copy paste it in here. I'm pretty sure we'll need all of these things, right? So we'll need all of these things. So we'll already have arc shift. We need a rendering of this thing. All right, we need a rendering of this thing. So, and that should actually work out, I'm pretty sure. FLT max, so that requires float, if I remember correctly. Right, we need anything else. Okay, so rate, do I not have rate anywhere? Okay, so let's put rate in here. So this is going to be 1. Anything else? Okay, so that's cool. Wait a freaking second. Yeah, I remember that. raylib already has STB image linked with it. So I'm trying to link with other, yeah, so there's a conflict between STB image implementations and this thing. It's actually not a problem, if you think about it. So you can just say, okay, this is a header now. Oh yeah, we can just remove implementation and it will act like a header and it's not going to include implementation, so it's going to use implementations from the raylib. That's actually really cool, right? Yo! The idea of STB style headers is just so fucking genius. Because it accounts even for situations like that, right? So essentially, if you have conflicting, yeah, you just disable implementation. It's just like use one of the implementations that's already there. That's so cool. What the fuck? Yo. Okay, so this thing works. Can we now do image and just specify this thing? Yeah, there we go. So, and yeah, as you can see, it just like goes very slow because we probably need to optimize that stuff. You know what? I think we can... Oh yeah. Oh yeah, this is kind of cool. I can stop at any moment and just close the window and it will verify. Yo, this is actually convenient. This is way better. Yo, you know what's interesting? What if we had these small components in a library? Okay, so you have a gym, and gym is a separate thing. And then you have some sort of like for verification. So you could organize a loop. Okay, you start the gym, you do something in the gym, then you close the window, then we take whatever we trained in the gym, then put in the verifier, and it opens the next window. You check something in the verifier, you close it, and loop goes back and starts the gym again. So you have these small little like sub-applications, but they're actually library that you call from the from C. That's a very interesting workflow, right? So instead of like a lot of small applications, separate applications, you have a lot of small functions that sometimes start these windows and stuff like that. That's actually very interesting. Yeah, I'll think about that specific workflow. I think it's a very interesting workflow, right? So because it gives you a lot of flexibility in terms of like what you want to do, and flexibility is actually very important. Like I don't want to make it too rigid, if you know what I mean, right? I don't want to make it too rigid, right? So we're gonna have like a lot of small composable things. We'll see. I haven't decided how exactly we're supposed to work with this library. We're figuring things out as we go. Okay, so what I wanted to do, all right, so I wanted to enable the optimization, like so. Right, so let's build this entire thing. And of course, source opt array.env, boom. Like breakpoint for an n, yeah. So did it actually, wait a second. Did it rebuild? Yeah, it did rebuild. It actually rebuilt too fast. Okay, so I can restart some things, but it's a bit slow. It's going down. And it stops. And then we verify this entire thing. You know what? Can we actually make it smaller? I think one of the reasons why it could be so slow is because it's too big. Can we take like half of it? Right, so what if we had less neurons? What if we just had less of them? I think it's faster actually. And it still goes down. Yo, I think it goes down even better. Alright, can I make it even smaller? What about like 4? Okay, so is that a good one? It still goes down, what the fuck? And if we verify... Okay, so what if I give it more epochs? What about like 15 or maybe 100, right? So because we can actually stop at any point. Maybe I need to make the amount of epochs unbound because I can stop at any point. Right, so because I can just like do stop, close it, and it will just do it for me one more time. So I think it doesn't matter like how many epochs we have, but maybe having like a bound is still useful for like, so it doesn't overflow with memory, because it keeps consuming memory for, at least for drawing the plot, at least for plotting this entire thing. It didn't recompile? What the fuck? Excuse me. Did it not? So max... Was I modifying the wrong... I think I was modifying the wrong application. Was I modifying the gym? Yeah, I was modifying... Okay, so I need to close the gym. Right, so... God damn it, classic. Alright, so let me see. So let's just wait a little bit, and let's just like let it train for a little bit longer. Like, let's let it train. Let it train. What the fuck? I'm surprised that it's still improving. So it's kind of funny. It doesn't dip anymore, but it's still declining. So that means it's going for another dip. It's literally going for another dip. What the fuck? Or is it? I don't know. That's actually super cool. Okay, this is a like basically 50,000s. It's still going down, so it keeps improving and improving. Right. So it doesn't spike. Quite often, these learning process like to spike when it just like cannot kind of like fall into the local minimum. But it goes down. Right. Maybe we should try to verify this entire thing. It's kind of getting closer. Yeah. it kind of like takes a shape. What if we edit like more of these things? So let me see. So how many neurons we had? So we had 7 of them. Let's actually add maybe another layer. Right, so let's do 7 and 4. Right, so let's make it a deep neural network, right? So if you have more than one hidden layer, it's a deep neural network. It's so, look at how deep it is. It's so fucking deep. Oh my god. Right, it's the deepest. That's actually a lot of space where it can store the image, to be fair. But we can give it a try anyway. So let's see if it's gonna run anything. Okay, it's going down. Maybe it's gonna go for a deep. It's going for a deep, Yo, what the fuck? Yeah, I'm using Raylip. Yes. Alright, so it's like... It's going for another deep? Is it going for another? Yo, what it keeps learning. I really like the thing about neural networks, at least about training the neural networks, is that they sometimes find this like next energy level and they make a dip, and then they find another one, another dip, and they're just like, it's so interesting. Overtrained. Well, I mean, it's supposed to be overfit, right? So because we're trying to store an image inside of the neural network, so we literally plan to it's actually approaching 0. It's actually very close to 0. 0 is here, right? So I put a line in here, and in terms of like this thing, it's actually very close to 0. Is it going to actually act like an image? What the fuck? And like, I mean, this is not that much of a complex neural network, to be fair. Overfitting. I want to wait until it becomes less than 100th. I think it's doable. Okay, so let's actually verify it. I mean, it got a loop. What the fuck? It actually got a loop. I mean, not bad. Like, it's just like, yeah. It got it. Like, it couldn't come up with the second hole. Actually really cool. You know what I want to try to do? I want to try to save this thing as an image. What's a compression ratio? That's an interesting question. It's just like we can try to see. So essentially we have yeah, we can try to compute the compression ratio. Where is the scratch? So we have several matrices in there. So the weight matrix is 2 by 7, right? So that means we have the first matrix 2 by 7, another one 7 by 4, and 4 by 1, right? So this is basically the weight matrices that we have. For each of the layers in here, right, we have basically 7 biases, 4 biases, and 1 bias, right? And this is how many floats we have, right? So this is how many floats we have, and essentially how many floats do you need to store this image? You need 58 floats. Each float is 4 bytes. So this is how many bytes it takes to store that image, right? So the original image is actually 28 by 28, right? So 28 by 28. So this is how many bytes you need to store this entire thing. How do you do compression rate? Do you just take a ratio of this thing, right? I don't quite remember. Like, I'm not a compression person, right? So let me see. Do I have to do something like this? Yeah, there we go. So 30%. Is that what it is? Or is that the other way around? I don't know. Right. So so yeah, you wouldn't count the network weights. Why? Because weights is like one of the places where you store the information. Weights are the thing that takes space on hard drives, right? So it's literally the thing that takes space on the hard drive, so you count them by definition, right? So because we're trying to compress. But here's an interesting thing. so we're using 4 bits. But quite often I heard in machine learning, there's a thing called float 16, right? So there's a thing called float 16, and it's designed specifically for storing neural networks, weights and biases and stuff like that, right? So you basically sacrifice a little bit of a precision to save up on space, right? And essentially you can compress even more. So yeah, so essentially you can store this entire thing in 116 bytes. Which is rather interesting. So how big is the thing in PNG? Okay, 298 bytes compressed with PNG, and this is how much you can. It's actually, yeah, it's actually better than PNG compress. All of that is hand waving and kind of bullshit, but it's just like, it's kind of interesting, isn't it? Right, so this is how much it takes, like with PNG compression, right? We managed to improve that, but of course there's a huge loss of information, right? There's a huge loss of information, but not really. We didn't really train the neural network to like its full completion, right? Because it doesn't matter like how much you train it, it still takes the same amount of space, right? So maybe if we train it a little bit more, we could have, you know, yeah, had less losses, if you know what I mean. It's good, but encoding a big image would take forever, I guess. Yeah, I don't know, maybe. We'll see. But we haven't finished yet, right? So what I want you to do, I want you to save the, you know, the generated image, right? So the trained thing. So how can we do that? We can basically just generate it, right? And let's actually also upscale that thing, right? Also upscaled. PNG stores other garbage in the data. Oh yeah, that's true. Yeah, so the PNG format also has like a lot of garbage in there. Though this PNG maybe doesn't really store that much garbage because, yeah, I don't know. Anyways, so let me see. We can do out width, and let's say it's gonna be 512, right? So it's gonna be way bigger, right? So we're gonna upscale this entire thing. So what we're gonna do, we're gonna allocate some data for the out image, so out pixels, and we're gonna do malloc out width, though I'm gonna do the following thing. I'm gonna take a size of out pixels, alright, so out pixels multiplied by out width multiplied by out height, there we go. And let's also make sure that this thing is not equal to null. I don't know why I put this stuff in here. My language model is actually kind of tired today. Alright, so let's iterate through this entire stuff, right? So we already kind of iterated it, but here now let's iterate out, right? Out height and out width, like so. I suppose what I want to do a similar thing, but instead of image in here, I want to do out. Right, so we're forwarding the neural network and we get in the pixel, right? So we get in the pixel and we're going to be storing that pixel in out pixels y multiplied by out width plus x, and this is where we're going to be storing this entire thing. There we go, and we now need to save it somewhere. So to do that, we need the STB image right, so I already have it open, so maybe I can do this kind of trick. Boom, boom. That's pretty poggers. That's pretty poggers. Okay. So STB image right. I wonder if RayLib also provides STB image itself. Let's actually try to do that. It's like STB image right implementation. Right, STB image right implementation. Let's try to compile this entire thing. Is it going to complain about STB image right as well? It will. Okay, that's very interesting. So yeah, so we only downloaded the header. I wonder if RayLib comes with the headers. Okay, so it seems to be compiled, but I don't really want to do anything right now. Right, so RayLib include. I don't really see. Alright, so can I do grep STBI load or something? No, it doesn't really come with that. So It's really interesting. Like it comes with STB like baked into the library itself, but it doesn't really come with headers. You have to have your own headers, which is fine, I guess. Right? It's kind of. Does it even mention STB anywhere? Oh, it does. Okay, so that's very interesting. So what's that? Optional dependencies included. Oh, they even acknowledge. So it's not a bug, it's a feature. The fact that you have STB image symbols in there is actually a feature. Our textures, so it's like a... That's very interesting. I mean, it's kind of convenient as well. It's kind of convenient as well. So we got some subs. Yo, money. Thank you so much for a tier 1 subscription, Core Runner. I hope I pronounced your nickname correctly. With the message, is writing compiler high testosterone coding? I don't know. I've seen people making compilers with low testosterone in their blood, so I don't think it has anything to do with your hormones. But thank you for a tier 1 subscription. Anyway. All right. So what are we doing today? I forgot what I was doing. Yeah, STB images, right? So this is, right, essentially a feature, right? This is essentially a feature. And now let's actually try to save this entire thing, right? So STBI. Write PNG, right? So we're gonna write this entire thing and we're gonna provide out file path, right? Out file path. So this is out width, out height. So the amount of components, of course, is gonna be 1, right? So because it's like a grayscale thingy. So here we have a pixels, and stride in bytes is basically out width multiplied by the size of out pixels, right? So now, if this thing failed, we're gonna say something like printf, actually fprintf, std error could not save image as, there we go. We can provide out file path and return 1. And if everything was successful, we're gonna say something like generated as from as. So generated out file path from image. Maybe I should call image actually in, but I mean I already like have this prefix all over the source code, so I don't really want to spend too much time, you know, changing things in there. All right, let's go. So what we have in here, out file path is not even defined. Would you look at that? Okay, so let's actually define it. So let's say it's going to be upscaled PNG. Right, so let's call it like this. So let's try to upscale this entire thing. Okay, all right. So let's actually let it train for a little bit longer. Right. So because I want to like see, I want to see like an actual 8. So the problem with that 8 is that because it didn't have a second hole, maybe it just simply doesn't have, you know, enough neurons to put a second hole in there. If you know what I mean. Right, maybe we just need to give it more neurons, but maybe we just should let it like train for a little bit longer. I really like how it goes. I think it's pretty cool. Justifies the second hole. I don't really know how to justify it. You mean by justify like think how like neural network would actually put the hole in there. I don't really know how to put the first hole in the first place, to be fair. Through which mechanisms? Look at the numbers in the second hole. I think I saw numbers being smaller than loop around them, just not by much. Ooh, okay, so that might be the case. Okay, I'm gonna let it run until 100k, right? And just see if it's going to improve. Is it gonna go for another dip though? It's kind of difficult to see at this resolution. Maybe I should actually start throwing out some of the values in here. Right. So it's actually going really small now. I really like that, like in terms of cost. Okay. This bias is actually dead. I mean, this doesn't really mean that the neuron is dead. It's just like the bias is 0. That means it doesn't really need to move anything anywhere. Okay, so that's a pretty good cost, I think. That's a pretty good cost. I don't know what's up with these sort of like pixels in here. Maybe it's a Rayleigh bug. Okay, so let's actually try to close that. And I mean, it does look like 8. And those things are definitely smaller than the nearby one, like 54 and stuff like that. And that's really close to 8. Okay, let's take a look at the upscale image. Right, so I'm gonna do fec b black. That's actually kind of cool. What the fuck? Yo, that okay. So wait a second. Can we take a look at the original? Right. So can we take a look at the original? It's so freaking cool. Wait a second. Okay, so this is the original, pixelated and shit. Right. So this is the original, and yeah. And this is basically. It's yeah, there we go. This is what this is how our neural network behaves. It looks like a phantom. This is so fucking cool. So that means it actually stored the image inside of the neural network in the weights and biases and shit like that. This is so cool. And second hole is actually visible. Yeah, it's just like more gradientish and stuff like that. And it's just like, yeah. That's so cool. It would be, okay, so as the chat said, somebody in the chat, I don't remember who, but it would be kind of cool to see how it like learns that like in real time. Because we saw that it starts like a blob. And I suppose then over time, that blob takes a shape of that image. Can we see that in real time? I think we can. We have the technology. We have the technology. We just need to like render this thing, right, on the window, right? And since we literally copy pasted the gem, we can just hard code that, right, and at least see something in there. All right. So I think we got some subs. We get some subs. Thank you so much, GR Camargo. I hope I pronounced your nickname correctly. Thank you so much for tier 1 subscription. Thank you, thank you, thank you. In 2023, we have the tech to see images exactly, right? But the question is, how do you draw goddamn images in Rayleigh? All right, so let me go to Raylib and do Raylib. Do you have image? Okay, so pixel data stored in CPU RAM. Ooh, and then you have texture. Data stored in GPU. Ooh. Okay, so it's kind of like SDL in that regard, right? So you have the CPU thing and GPU thing. And I suppose you compile one thing into another one, right? So can you draw an image right away? You can't draw an image. Can you draw a texture? Texture. You can draw a texture. Look at that. So that means you need to be able to construct a texture, right? So let me actually find a thing that starts with the texture. Actually, texture, I don't see. So the start of this thing, doesn't find. Failed wrap. Okay, texture 2D. Let's find some functions that. Oh yeah. So because it starts with RL API texture. Okay, so you can load the texture from a file. This is not what we need. Right, this is not what we need because we're going to be generating texture on the fly. Right, we're generating texture on the fly, we don't store it in the file. You can load the texture from an image. Okay, so that's already better. That's already better. Can we just supply the pixels? You can update the picture through the pixels, but it's not really what I want. Okay. So a render texture, there's also render load texture for rendering frame buffer. So frame buffer is usually like a back thingy, image draw. There's no such thing as image draw. Okay, so and can you construct an image, create image? Maybe there's something like load image. Okay, so, and you can load image from file, and this is basically STB. Oh, okay. So instead of using STB, we can use Raylib actually, because it wraps STB basically like that. You can load image from a memory, maybe that's what we need. Not really. Oh, okay, so you have to provide the file type, because you load like literally format, so you can't really do it like that. Can I just give you the pixels and generate an image out of that? Okay, I can generate an image like with a solid color. Okay, maybe that's how you create it. So I can just generate a image of that specific size. Can I then like set a pixel with this thing? Let's actually go ahead and try to generate an image. Like, let's do it like this. So right before the start of the loop, we're gonna do, let me think. I think I'm gonna be using the original width and height. I don't really want to upscale it, because it's like, it's a lot of pixels to render if you think about it. 412 by 412. It's just like, yeah, this is how many pixels we'll have to render on each frame, and I don't think it's gonna be too fast. Right, I don't think it's gonna be too fast, so I think I'm gonna keep it like very small when we're rendering in the real time, if you know what I mean. So in terms of color, I'm gonna put black in here, right? So preview image, right? So this is a preview image, so that's what we get. So how can I, is there something like put draw? Oh, you can, okay, so you can draw a pixel. So that means that on each of these things, so here we are rendering this thing. So we actually need to allocate a little bit of a space on the screen, right? So right now we divide the screen into by 2, and on the left we have the plot, and on the right we have the neural network. So what if we actually divide it by 3, right? So here I actually constructed it so it's super easy to just add more widgets, right? So the width of the single image is a third of the screen, so we put 1 in here, then we shift our X by the size of the widgets, and this is where we draw the third one, the second one, and then since I made the width smaller, we're gonna have a little bit of a space for the third one, so that should actually work. So let's give it a try. There we go. Yeah. So this is where we're gonna have a third one. So it's super easy to just like add more things in here. So I did that intentionally, just in the future if we want to add more things. Maybe we can also realign some stuff. Maybe it's gonna be vertical, I don't know, but yeah. So I really want this thing to be like a more general purpose framework where, depending on your model, you can just like make arbitrary configurations of different widgets, right? So because some of the models, they require 2-dimensional image, some of them may require 3-dimensional objects or something like that, and it just like depends, right? And you just like in the program, you basically define what kind of widgets you're going to have for your model and where they're going to be located and stuff like that. So I think that makes sense. Maybe for your model you don't need to display the neural network itself, right? But it's, to be fair, the neural network itself, like the showing the weights and biases, is kind of useful. It just like looks cool, right? Especially when it just finds the energy level and just like drops down, like at this point. And they start to like highlight and stuff like this. As you can see, they start to like light up. It's kind of cool, but that's about it actually, right? So it doesn't really provide any useful information, to be fair, right? By itself doesn't really provide any useful information. How the image is upscaled. The image is upscaled. Yeah, this is actually cool. This is blob. By essentially training the neural network on the normalized coordinates. So the coordinates that we feed into the neural network are not the real coordinates, they are coordinates from 0 to 1. So that way, if we need to upscale it, we just like multiply it by a bigger value. So since they're normalized, we can remap all of these coordinates to any arbitrary size, and effectively what the neural network will do, it will just interpolate between these pixels, right? That makes sense? Okay, nice. So, yeah. since neural networks are like function interpolator, what I would expect it will do between the pixels is essentially just like interpolate between them and like make them smooth. And this is exactly what we saw when we rendered that 8. Right, but I think it overrode it already. Right, yeah, there we go. So this is how it looks like mid-training. Look at that. Okay, so I need to make the background black because it ruins the, yeah. So this is how it looks like midway. It's kind of interesting. It's like this blob. Oh, so cool. And it kind of like looks like generally like the shape of that 8. So anyway, let's continue. So what we want to do, right, on each iteration, so we left a little bit of a space for this thing. Now we need to render this entire thing. Okay, so here we're just like rendering from the neural network, right? So we're rendering from it. We get the pixel, and what I need to do, I need to just put that pixel in there. So where is the arraylib image drop pixel? Okay, okay. So image DST, preview image. So the position is X and Y, and the color, oh yeah, the color is gonna be, but what we can do, we can use collateral, right? And essentially, we can take that pixel and repeat it 3 times. And alpha, we can set alpha to 155, right? So we have a usage for collateral. I really like this macro. I really like this macro. Collateral. Anyways, so, alright. So preview image, I mean, you're supposed to put it like that. I think I should not run this stuff in here. Can I just comment it out? Yo. Yeah, I just commented out like half of the comment. That's actually very useful. Alright, so arraylib. But now I need to basically construct texture from image. Alright. Is there any update texture with new? This is a really weird API. Right, you can, okay, we can load the texture from image. Right, we can load texture from image. So let's actually try to do it like that. So something weird is going on. Oh, this is, okay, so I was wondering what the hell is going on. I just like had this comment that I couldn't see. This is a preview texture. This is a preview texture, and we're making it from preview image. But the question is, how now I update the texture, right? So one of the things I have to do is draw texture. Okay, so that makes sense. Can I scale this entire thing? Because it's going to be 20 by 28. It's kind of small. Does it have a arbitrary stuff or scale? Okay, so there's this thing. We can scale it maybe. So this is gonna be preview texture. Ooh, this one is interesting. So this one is interesting. How are we gonna define the position? Position is at Rx, Ry. Right, so this is this thing. Can I do collateral? One more time, and just Rx, Ry, so this is where it starts. In terms of rotation, I think it's going to be 0. In terms of scale, I don't know, we can multiply it by 10, and tint is going to be white, right? So, collateral. Okay, so that seems to be compiling. So, but I don't think it's going to work, because we literally need to update. Yeah, okay. So, on top of that, it's kind of small. Let me actually do 20, first of all, and also after we render this thing, I'm gonna update Rx. Is it going to work now? It doesn't update it. Right, so let me see. Update texture. Texture. What was there? I forgot. load texture. Yeah. So let's update and pixels. And where do you get the pixels from? It's just like so weird. Okay, array lib update texture example. Literal is too much to type. Make a cleat macro. We should suggest that to Ryzen 5. Yes, at some point. Okay. Texture processing. Okay. Update texture. Okay. You load image colors. What is load image colors? Load image data from image as color. Ah, but why do I have to do that? Can I? And it returns the pointer to the color, which actually raises the question: why update texture then doesn't accept the pointer to colors, and it accepts void star? That's a very weird question. Because, or maybe because it does not necessarily has to be, yeah, somebody said RGBA array, right? It could be, it not necessarily has to be a color, right? It's like anything that is 4 bytes, right? Or maybe the format of the texture. So that means I don't really need an image. I can just pre-allocate the array of colors and just fill up the array of colors and then update the texture. But then the question is, how can I construct a texture from the size? I can construct a render texture of a certain size, but the only way I can construct just the texture is... That is weird. So you can gen texture meep maps. And then you unload image colors. This is the weirdest... How can I just create an empty load texture? An empty load texture? But maybe I can just... can I just like provide data? I think I should be able... Like loading and unloading is kind of dumb. Alright, I think I should be able to just use the data of that image, right? So update texture. So I don't really know why in that specific example they're like loading, unloading, probably copying some shit, like why? Preview image. That's a really weird API, not gonna lie. It's kind of complicated. Probably because of the underlying OpenGL or some other GPU APIs that make it complicated, right? So that's probably... Okay, so this is more of a... Alright, that's interesting. I think it's too big. So it's not black anymore. That's what's interesting, right? It's not black anymore. It's grayish, so that means it's kind of working. So let's make it like maybe 15 because I want it to be able to fit on the screen. So it doesn't really automatically resize, unfortunately. I think it should. Right, I think it kind of should. Okay, so it's actually perfect. Okay, so let's try to train. Okay, so it's moving. Can you see anything? What the fuck? Yo, this is so fucking cool. What the fuck? It's like... It's fucking emerging. It's literally emerging out of nowhere. What the fuck? This is so cool. I'm waiting for another dip. For another dip, it's going to probably... Look at that. What the... This... It's trying to figure out the hole. It's trying to figure... Yo! Look at that! It's moving the... What? Did you see that? Like, it figured out a hole, and it wiggles the hole around, trying to fit it so it minimizes the cost function. This is so cool! So it figured out that it can put like a positive blobs, and then it figured out that it can put negative blobs, and negative blobs is like a hole, and it just tries to like position that hole. This is so cool. Like, it's kind of cool to see how they're actually learning. Like, okay, we can always restart this entire thing and just like try to see one more time. It's kind of slow, especially when I'm streaming and stuff. But like the way it appears for the first time, and you can see like when it like deeps down, right? It's just something starts to change, right? This looks pretty much exactly like when you use Midjourney to generate picture out of text. Really? I never actually used Midjourney. I just realized that I never used any of these text-to-image models. Maybe that's like very much inherent to how they work. Oh, man, this is so fucking awesome. I wish it was a little bit faster, but I mean, yeah. That's so fucking cool. What's the input? I think we need to actually render the input. The input is 8, right? So we're trying to make it act like 8. I suppose it would be nice if we... Yeah, if we just like tried to render it as well. So here we have a scale, right? So this is the scale, which is 15, obviously, right? So draw a texture. So we update the texture with the preview data, and unfortunately, yeah, the original data is 1 byte format, so that means we have to probably regenerate this thing one more time. Okay, so this is gonna be interesting. So we're gonna take the original thing, image pixels, right? So this is going to be y multiplied by image width, of course, plus x, and this is going to be that, and we're going to simply repeat that thing second time, but we're going to actually place it a little bit down, right? So essentially we're going to say plus, and what's going to be the height? The height is going to be image height, but multiplied by the scale. Right, so we just like moving it down so we can see them both nearby. Though it would be probably nicer to swap them around. Right, so I think it would be nicer to swap them around. Yeah, so we can see both of them. Can we see shit in this mist? We can't. This is bullshit. So, alright, so here we are. Yeah, I see. So you effectively you need to have 2 separate texture then. You need to have 2 separate texture, but I mean I don't want to spend too much time on that, unfortunately. Alright, so not really in the mood of going there right now. So we can try to do other images maybe. Right, so do we have... Oh yeah, so it's still open. So can I take a look at like 6? Let's grab this one. That's a very interesting one. Save image as. So it's learning, as you can see. All right. And where do we have these things? So this is 6. Okay. So that means we can do 32. So let's see how it is going to learn the 6, if it's going to learn it at all. At least the cost function is going down. So the thing about neural networks sometimes is that it feels like they're not learning anything until they're starting to deep down. Okay, so this is... Alright, so it kind of like roughly figured out the shape of this entire stuff. So let's see if it will figure out something more. Right, so it's trying to do this 6. All right, so we're going for another tip. So it's figuring out the holes, right? So it figured out that you need to put the hole in. That's not fucking bad. All right. All right. So it found something. What the hell is it trying to draw, monkey? Yes, okay. Well, okay, so it's kind of close. It's just like it needs to figure out to put thing in here for it to work. So let me. Right, so this is basically what we have in here. Right, and it's trying to learn. Yeah, it couldn't figure out to put like a breach in here. Right, but it's really close in terms of like trying to replicate this thing. It's still going down, the cost is still going down, so I think it may figure out eventually that you have to put something in here. It's actually getting closer to the limit of the epoch, so I think it may not figure that out, but it may try to figure it out from a different point. Alright. I really want to try this thing off screen when I'm not streaming, because it's supposed to be faster actually. It's supposed to be faster. Okay. So it found a different way of drawing this entire thing. Now it's filling up this thing, but then it will need to figure out that you need to put like a hole in here. So this is the image that it's trying to replicate. It's really struggling with that part. It's a really complicated part because it's like a hook. Yeah, it's just like, but it's trying. It's trying. I think I already do 03, don't I? Yeah, I already do 03. Yo, it kind of... Okay, so it's starting to... Yeah. It's stuck. The cost function is actually kind of jumping around. It's pulsating. Yeah, it's having a hard time to replicate that. Yeah, but this is like this is the closest it could do. And I suppose what it's doing is just like replicating it with like curves. Right. It's basically approximated it with curves, smooth curves. Right. And they're smooth because we're using sigmoid. We're not using ReLU. Maybe we should try ReLU, but that's probably the topic for another time. Right. So I need to try something. It's actually really cool. What if we... Okay, so let's actually go back to the original 8, right? So it was the... Yeah, 57. The original 8. What if we try to make the neural network even smaller? So here we have 7 and 4. Can we just like cut this amount of neurons in half? Because the less neurons we have, the more information we basically compress effectively, right? So can we have 2 neurons in here? Right. Is that a thing we can do? Right, so this is a much simpler neural network. Will it be able to approximate the 8? Well, at least it got the general shape, right? But will be... does it have enough like power to put a hole in there? It may not actually figure out, but it's getting there. Right, overall it got the shape. Okay, so it has a capability of putting a hole, right? So I thought maybe with the less amount of neurons it won't be able to put holes anywhere, but it figured out that you can put a hole in here. So that's very interesting. All right. And what's cool is that this is the entirety of the neural network. Right, this is the entirety. Like we can see it, like how much information it actually compress in here to get this image. Right, so this image is compressed into this thing, into this little device. This is actually so cool, if you think about it. It kind of got it. We can actually stop and then just close it and upscale it. And if we take a look at the upscaled version of this thing, right, so this is upscale. This is how it looks like, right? So it's very like smoothed out, everything. So we can actually generate like any resolution, right? Because the coordinates are normalized and stuff. Right, so what if I make it 4? So it's a very small neural network. Will it be able to approximate like anything at all? Right, so how small can you get it? Okay, so it's doing things. You can draw at least line. Right, that's already something. Okay. It actually learns fast. Well, probably it learns faster because it's just like smaller, right? So it's computationally easier for it to like figure that out. But it's less capable, right? So it has like less neurons to work with and to modify things. But the cost's still going down. It's kind of crazy how it converts storage usage into computing power. Yeah, I guess. Oh, it's interesting. If you take a copyrighted image and you train a neural network on that copyrighted image, and then you reproduce that image with the neural network, does the copyright still applies? Or the neural network just created the image and got inspired by training data, just like humans are. They're like humans. They got inspired and reproduced that image. You know what I mean? In Germany, yes, it's still, well, I mean, I'm pretty sure it should be copyrighted, right? So it's just basically storing the same image, but in a different form, right? But no, look, the neurons, they're just like a human neuron, so it didn't it got inspired by the image and reproduced the image, just like a human did. Finally, we made the artist obsolete. So let's actually make it maybe a little bit bigger. Can we just make it? So the bigger I make it, the more computation difficult it becomes. Neurons have feelings too, exactly. Yeah, it's super slow. Well, one of the things we can try to do, do stochastic gradient descent, right? Stochastic gradient descent. But I didn't think, like, we don't really have that much data, so the problem here is not really the data. Yeah. It's doing something. Just slow. But it has a lot of information to store this thing in here. So people are asking about the source code for this entire thing. It's available at nn.h, right? So this is what we're developing here. Yeah, so it's, yeah, we already have that in the chat. We already have that in the chat. All right, so that's pretty cool. So this result so far is the best. It will be kind of interesting to explore, you know, several colors, right? So essentially, if you give it more outputs, right? If you give it more outputs, it will be able to also reproduce the colored image as well, right? So it will be able to do that as well. It will be kind of interesting. Sometimes I feel like this is basically like converting raster image into a vector one. Yeah, it's kind of like, yeah, it's turning raster image into a vector one because it's like a bunch of like curves. We're approximating the image with a bunch of curves. It's crazy how we started from explaining math basics to this. Yeah, because that's how it starts, right? So journey starts with a small step, right? With the first step. Trying to sound pretentious. I don't know if I managed to do that, but yeah. All right, I'm definitely gonna try like run this thing off screen a little bit more. All right, because the off screen is gonna run a bit faster. So maybe I'm gonna actually commit whatever we have already, right? So we're gonna commit whatever we have already. So I'm gonna commit this. So in terms of gym, I don't want to modify the gym. I'm gonna commit image to mat. Maybe I need to rename it to something else, but I'm not 100% sure. Right. So I'm probably gonna reorganize everything in here. So, but I'm gonna commit whatever I have as of right now. So, but after this stream, I'm gonna reorganize all of these things. Right. Implement image to neural network compressor. Let's put it this way: implement image approximator. Right. I think it's a better name for this entire thing. So if you want to play with this kind of thing right now, you'll be able to do that. Okay. So forgotten build.sh changes. Right. All right. So we've got some subs. That I want to acknowledge super quick. Thank you so much, MHSF777, with the message "need to understand 69 and say nice." Was it only? I thought maybe it's because you have 69 month, but yeah. Thank you so much for tier 1 subscription. And Twisty, thank you so much for Twitch Prime. All right, isn't that a poggers? My friends? I think it's pretty freaking poggers. I'm already streaming for 2 hours and I didn't make any freaking break. That's insane. So I was so preoccupied with this shit that I forgot to make a cup of tea. Right. But this is so cool. There's also huge potential for this thing. Right. Imagine actually like compressing this thing into neural network and writing WebAssembly program, right, that accepts images in this format and renders them in a web page, right? So imagine using that to compress images on a web page, right? So you have a JavaScript that downloads a neural network instead of an image and gives it to WASM program that uncompresses the image by actually simulating the neural network, right? So does anyone have any questions? How do you deal with burnouts? I just don't. I'm burned out all the time, even right now. What are you building? I'm just experimenting with neural networks. I'm just trying to learn how a neural network works, just to, like, you know, have an idea of what they are. And I kind of like that because they feel like a different paradigm of programming, right? A paradigm of programming where you're not writing the code directly of the thing you're sort of like solving, but you're describing how a model has to behave, and the learning process sort of like finds the model that fits your description. And in our case, the description is an image, and we just told the learning process, now make a model that acts like that image. And it's actually a very good approximation. Look at that. It's basically 8. It figured it out. Look at that, it figured it out, literally. What the fuck? I think this is the best result we've got so far. I wonder how many programs do you need to, so AI trained to recognize digits out of normal image can also recognize digits in reconstructed images? That's a good question, I don't really know. Yeah, after 100,000 of iterations, it finally figured it out. So, and we can now close this entire thing and look at this verification. So yeah, and let's take a look at the upscaled version of this entire thing. So we upscale the image. That's a very good high quality upscale of the original image. Definitely better than bilinear interpolation. Who fucking needs bilinear interpolation? I'm gonna show you how bilinear interpolation looks. It looks horrendous. Right, so just a second. Right, so I think it uses bilinear interpolation here. So this is how bilinear interpolation looks like. It still looks pixelated, but look at this beautiful neural network interpolation. It's much smoother, right? So you see, here is the bilinear interpolation, and this is what our neural network managed to come up with. It's way better, way smoother, high quality. AI is the future. AI is the future. It looks like we turned on RTX in Minecraft. Exactly. Well, it's kind of, yeah, it's kind of cool, right? It's kind of smooth. I really like how it, like, if you disable the interpolation in here, right? So this is the pixels, and there is sort of like this, sort of like a thing that comes out, and it picked up on that. Look how it picked up on that thing, and it also picked up on this thing. It's just like so funny how it picked up on them. That's so cool. Oh. Yeah. Alright, so that was a fun stream. I guess that's it for today. Thanks everyone who is watching me right now. I really appreciate that. Have a good one, and I see you on the next recreational programming session with Azuz. Alright, so see you next time. I love you. Mwah.